So the goal of this tutorial is to show how LTspice can help you understand what's going to be the variation in a circuit's behavior when temperature changes. We all know that electronic circuits, typically they are supposed to be operating at room temperature, but then either due to a variation in the ambient temperature or due to the self-heating of the circuit components, the temperature of each individual component on the board is going to change, and as a consequence, the electrical performance is going to show a variation as a function of temperature. LTspice allows us to evaluate how the behavior of a circuit changes when the temperature of the component changes. And this is kind of interesting to study some circuits, especially whenever you would like to have a certain stability of the output current or of the output voltage, for example. We will start with a relatively simple circuit, which is a circuit based on a Zener diode. We're going to use a specific diode, which I'm going to place on my schematic over here so that we can see it. And so I will put here down a diode, and the diode I'm going to show and to choose is obviously a Zener diode. So I will sort the diodes by type. I will go look forward Zener diodes. And the Zener diode I'm going to choose is this 1N750. This is a 4.7 volt Zener diode, which has a typical current of 20 milliamps. I just took a note here so you can see the value. Of course, I need to bias this diode. And in order to bias the diode, of course, I'm going to use a resistor. And I will also use a resistor as a load that I will put down here. So these are the components I'm going to use. And in a minute, you will have a chance to see what I'm planning to do with this diode. Of course, in order to drive my circuit, I will need a voltage source, which I will put down here. Let me now connect the various terminals. So I will press F3 to put down the wires, then left click whenever I need to put down a connection. So this is the first connection with the resistor R1. The resistor R1 will bring the current to the diode, to the Zener diode D1. And in principle, if I close this circuit in this way, that circuit is already a good way of saying things. The voltage source is giving a voltage to the resistor, and then the current will be flowing through the reversely biased, if you want, Zener diode. And then, of course, the connection is complete. This can be seen also as a voltage regulator. So in principle, you know, a Zener diode fixes a certain voltage, and so that voltage can be, for instance, transferred to a load, which is exactly what I'm going to put here. The resistor R2 represents the load of this circuit, which is a resistor basically across which I would like the voltage to be equal to the voltage across the Zener diode. So the way we can say the circuit is as a voltage regulator, as we said, so we have an input voltage here, then of course we have a certain drop on this resistor, and then the Zener diode will fix the voltage across the resistor R2, which can be seen as a load. Of course, for the simulator to work, I need the ground connection to be placed somewhere, and as usual, I will connect the ground to the minus connector, to the negative connector of the voltage source. Now, let me choose a proper value for this voltage source. For instance, I will choose a voltage of 6 volt. And now at this point, you see I have 6 volt in the voltage source, and the Zener diode, if properly biased, and I have taken this information from the datasheet, will have a voltage drop of 4.7 volt and a typical current of 20 milliamps, which is flowing through it. The load resistance is relatively large. We are considering having 30 kilo ohms for the ohm resistance. So whenever the output voltage is 4.7 volt, only a fraction of milliamp will flow here. And this is going to be considered a relatively negligible current. Now the point is that the resistor R1 has to be chosen, the value of that resistor has to be chosen as such that the current which is flowing through it is approximately equal to the typical current of the Zener diode that I need for the Zener diode to be driven at the proper bias. And if I look at the datasheet, when the Zener diode is supposed to have a 4.7 volt Zener voltage, its typical current has to be 20 milliamps. So the calculation is quite simple because we have 6 volt in an input, 4.7 volt on the output, and I need the current on this resistor R1 to be equal to 20 milliamps. And if I do the math, it's relatively simple to find out that the value of the resistor has to be equal to 65 ohm. Of course, in a real circuit, you wouldn't have possibly all possible value of the resistors, so you would have to choose the nearest value, but in this case, we're just simulated. So in order to show what the results are, I will just put here 65 ohms as a value of the resistor. What I plan to do is a simple DC operating point simulation. So I will go on simulate, edit simulation command, and of course here I can choose transient, AC analysis, DC sweep, and so on and so forth. I will choose DC operating point. And the directive, the very simple directive .op will appear. And I will put it here, attaching it near to my schematic. Now I'm ready to run my simulation. And if I run my simulation, this summary will come out. The input voltage will be equal to 6 volt, which is the voltage I have here. The output voltage is going to be equal to 4.7 volt, which is exactly what I would expect from my diode characteristics. The current through the diode is effectively very close to this typical current, so I have done proper calculations. Approximately 20 milliamps, and it's approximately equal to the current across the resistor R1. The small difference being the current which is flowing through the load, which is 0.16 milliamps approximately, the current which is flowing here, which I have neglected. And of course, if you are a good student, you would then check out the data sheet of the diode to verify if this assumption, to neglect the current through R2 for sizing and dimensioning R1, is a good choice. And then, of course, I will also notice that the current which is in the output current of the voltage source is identical to the current which is flowing through the resistor, because that's perfectly reasonable since the current is flowing through this node. Now, of course, our circuit that, as we were mentioning, can be seen as a voltage regulator, is able to regulate the output voltage at 4.7 volt approximately at room temperature. But the question is, how stable would that output be if now we are changing the temperature of the circuit? So let's try to see this. To do so, once again, we use a SPICE directive. So we click here, and the SPICE directive is this box that gives us the possibility of writing a directive directly to SPICE that can be then executed by the simulator. We will try two different directives. The first one is .step temp. In this way, we're going to make a variation in temperature. And we can, for instance, do that by providing the simulator a list of temperature values. It can be, for instance, 10, 30, 50, 70, 90, 110, 130, 150. In this way, I am telling the simulator to do a list, to repeat the simulation on this list of temperatures between 10 and 150 degrees centigrade. I can then attach my directive to my schematic, so it's visible. And now the only thing I need to do is to repeat my simulation. So I go here, I click on Run, and my output plot will come out. As you can see here, on the horizontal axis, I have the temperatures in this case, and on the vertical axis, I can put whatever parameter I want. Of course, the first thing I want to put to see and to check is the voltage here. That voltage is not changing as a function of temperature because that's a parameter that I have set as an input for my simulation. I will now remove this trace, and I can now give a look to the output voltage. So I will click here. the output voltage of my circuit, which at room temperature is supposed to be equal to approximately 4.7 volt, as we were mentioning, we see is linearly, almost linearly, decreasing with temperature, indicating that the ability of my circuit to regulate the output voltage will be changing a bit. And this is typical for a diode regulator, because eventually we know that the characteristics of a diode will change as a function of temperature, as temperature is increased. This is an example. Of course, I could have chosen also different possibilities. So if I want to right-click here, I can change once again the way temperature variation is obtained. I have chosen in my previous example the least option. I can also use a linear variation, for instance, but with a start value, for instance, of 0 degrees centigrade, a stop value of 110 degrees, and an increment of 20, or better, of 10, if I want to do that reasonably. And if I do so, you see, at that point, I don't have the list anymore, but as we have seen also with the parametric simulation, we have the possible start point, end point, and increment value. And if I run the simulation again, you will see, okay, the result will be quite similar because we can expect that. And we will see the interval has changed in this way. And this is the way a temperature-dependent simulation can be done.